Hello friends, let us resume our discussion on the first law of thermodynamics. So in the previous lecture, we expressed the first law of thermodynamics in the form of a simple relation. So this simple relation that rather encapsulates the first law of thermodynamics is of this form, wherein on the left hand side we consider the change in the internal energy of the system, and this is brought about by the combination of the heat transfer into the or out of the system and the work done on or by the system. So this is what the first law of thermodynamics, the way we have considered it or the way we have expressed it. Now if you consider it closely rather, like we stated in the previous lecture, this first law of thermodynamics, it rather encompasses the whole approach that we take in the field of thermodynamics. That is, when we consider what thermodynamics means, the introductory part of the thermodynamics, we saw that the thermodynamics is unique because it treats work and energy in a similar way. It treats work and the heat energy in the same form, or it treats works as a form of a transfer in energy or transfer in heat energy particularly. So far, even though we have considered it, we have just using some verbiage, we have talked about it. We have not arrived at an expression that related work and heat energy in a single, in the combination of different terms in a single expression. And this single expression is introduced to us, or it is rendered to us by the first law of thermodynamics. Now, ideally, the best way of representing this expression would be the change in the internal energy when you have a system that allows for the heat to transfer, and also the system is able to do some mechanical work or to observe some mechanical work. So the combination of the heat energy and the work brings about the change in the internal energy of the system. So it is the combined effect. It is not one getting removed by the other, but it is the combined effect. So the ideal way of representing it would be the combined effect of work and the energy transfer or heat energy transfer. The reason we introduce the negative sign here, the reason the negative sign is brought here is because of the unique convention associated with the work. So the work, when it is done by the system, since there is a volume expansion, even though the energy is being expended, since there is a volume expansion, and given the volume expansion would render us or would give us a positive change in the volume, the entire work is treated as positive. And whenever the work is done on the system and the volume change is negative, then the entire work is treated as negative, and that is the reason why we have the negative sign as the prefactor. So the ultimate change in the internal energy of the system that helps us understand this change in the state of the system when a combination of heat transfer occurs and a work is done on or by the system, it is given by the first law of thermodynamics. It is the combined influence of heat and work done. Now, we saw that a conventional way, or rather based on the canonical description of work, we can describe the work done on the system or by the system as the product of a constant pressure and change in the volume that occurs as a consequence of the work done. So the work done can be quantified as the product of the pressure and change in the volume, and this assumes that the pressure is constant. So this canonical, the standard description of work comes from the standard description of work done in the Newton's laws of motion on Newtonian mechanics, which is nothing but force into displacement. We are replacing force with pressure here and the displacement with the change in the volume here. Now, when we consider this, what essentially we are doing is we are considering just one variable, or the work done is dependent on the variable V. And similarly, we began the discussion on the first law of thermodynamics with considering a system that allows for the work to be done by the system or on the system, and that allows for the transfer of heat. And the way the change in the state of the system is being measured by us, or the way we are able to discern the change in the state of the system, is through the change in the temperature. Change in the temperature. So if we allow the volume of the system to change, then the work can be quantified. And if we measure the temperature change, we are ideally estimating the amount of heat transfer. So essentially then we can express this amount of heat transfer, or we can state that the amount of heat transfer is dependent on the temperature change or the temperature of the system. So essentially what we have is, of course, these are dependent on dV, that is change in the volume, and dT, that is the change in the temperature. The amount of work done dependent on dV, and the amount of heat transferred or into the system or away from the system is dependent on, or it can be estimated based on the change in the temperature dT. So ideally, since dV and dt are state variables and they are nothing but the difference in the final state and the initial state, so we can represent these two as a path variables that are dependent on the state variables. So the accurate depiction of the dependency of the work and the heat on the volume and temperature should be represented in this manner. That is, the work done is dependent on change in the volume, and the heat transferred within or out of the system is dependent on change in the temperature. However, since the volume and temperature are rather state variables and they are nothing but difference in the initial and rather difference in the final and initial variables, it is possible for us to write it in this manner. So ultimately what we have is, we saw this in the previous lecture, that change in the overall energy, internal energy of the system, which was initially governed by the work done and the change in the heat that is being transferred into the system. So both these are rather path variables. So that means whenever we want to consider a change in the state, that is U2 to U1, given that these fundamental variables that ultimately dictate the change in the state are path variables, we have to consider them simultaneously. We cannot make any further simplification, so this needs to be considered simultaneously. However, since we have this relation that has been brought about by the conventional description of the work done and from our intuition of what happens to the system when the heat is being transferred, we are now able to express the change in the internal energy of the system that actually dictates, or actually it explicates, it unravels the change in the state of the system in terms of temperature and pressure. So what essentially we have is, we have for a given temperature T1 and P1, we have a specific internal energy which we refer to as U1. So based on this understanding alone, we are not talking anything about or concretely we have made some assumption and we are trying to replace the path variables with state variables for our simplification. So we are not stating anything holistically. So what we are considering is, we are trying to change the variables that govern the internal energy of the system. And so in that case, what we observe is, when we have a specific combination of the state variables, it gives us a specific state. And so in case of T1 and P1, it gives us a specific U1. Actually we rather made a mistake here, so it should be V1. So variables that we are considering are P, volume, and temperature, so it should be V. So for a specific combination of T1 and V1, we have a specific internal energy. Again, in this context, it is not rather objective. In this context, we have this combination. So the U is being related, or what we have essentially done is, we have now changed the fundamental variables that govern the internal energy from path variables to state variables. Now let us take few steps back and consider our different variables, our distinction between independent and dependent variable, which we made while we considered the combination of temperature, pressure, and volume. So during in the first few lectures, particularly in the introductory module, we related, in order to make a distinction between dependent and independent variables, we consider the combination of temperature, pressure, and volume. So let us consider what we have seen in those discussions. Let us consider a few key points what we have seen in those discussions, as it will be hugely helpful for us to move further from this point where we are in now. So the point where we are in now is we have expressed the change in the internal energy of the system in terms of temperature and volume. Now in the previous discussion we saw that we treated volume as a dependent variable that depends on temperature and pressure. So for a given combination of temperature and pressure, that is T1 and V1, we would have a specific volume, that is V1. And if you want to change this V1, then you need to change either temperature or pressure or both. So for a specific combination of the independent variables, that is temperature and pressure, there is one state of the system that is dictated by V1. So when you have, even though you have three variables, two of them are independent, and when you fix these two independent variables, the overall state of the system is fixed through the volume. So therefore, whenever you want to change the volume, you need to change either one of the independent variables, both these independent variables. So when you fix these two, the system is in equilibrium state or stable state, and in order to move the system from this state, you need to change the independent variables, either one of them, one of it, or both of it. So this is often referred to as the Zeroth Law of Thermodynamics. So by way of passing, so this is something about the Zeroth Law of Thermodynamics. So what we saw during this context, during while we discussed about the dependent variable and independent variable, we saw that since the overall state of the system is described by the state variables, the change in the state of the system P2, which is characterized by temperature T2 and pressure P2, which is this state, we arrive at the state from V1, and in order to arrive at the state, we have changed both temperature and pressure. Now, since we are using state variables to describe the state of the system, and the state variable characteristically their change just depends on the initial state and final state, it does not depend on the path, it is possible for us to introduce an intermediate state. So this is something that we considered earlier. Now when we introduce an intermediate state, what it allows us to do is, it allows us to consider or fix one of the variables and change the other variable. So we take a detour, instead of moving from V1 to V2 by changing both temperature and pressure simultaneously, we are taking a detour, we are considering an intermediate step, and so here it is V1 rather. So in order to arrive at this intermediate step, we are just changing the pressure alone and ensuring the temperature is constant. So by this pressure is now changed to the final pressure that we are interested in, while the temperature is assumed to be or is fixed to be constant. So the intermediate step is characterized by the constant temperature but a pressure that relates to the final state of the system. Now as the second step, from the intermediate to the final step, what we have is, we ensure the pressure is constant, we maintain the pressure to be constant and change the temperature, thereby we arrive at the final state of the system. Now once we are able to introduce it, and once we are able to introduce an intermediate step that is characterized, that the way we introduced it in such a way, it is in such a fashion that the temperature is mentioned to be constant when the system shifts from the initial step to the intermediate step, and the pressure is maintained to be constant when the system shifts from the intermediate step to the final step. So this being theoretical, we have assumed our intermediate steps to be in such a way. So this introduction of the intermediate step has allowed us to express the overall change in the state of the system in a rather simpler manner. So the overall change in the state of the system, it is characterized by delta V, which is nothing but V2 minus V1, and now instead of going from V2 to V1, we have considered an intermediate step. So this intermediate step, like I said, it involves a constant temperature when the system travels from V1 to the initial to the intermediate, and a constant pressure when the system travels from intermediate to final. So because of this introduction of the intermediate step, what we have essentially done is, we have considered a constant temperature transition and a constant pressure transition. So the transition during the constant temperature can be expressed in this way. You have your temperature to be constant and the pressure changes from P1 to P2. So pressure is changing from P1 to P2, and during that the volume changes. So this is the change in the volume with pressure, and the temperature is constant. And similarly, we have a second step where the temperature changes from T1 to T2 while the pressure is constant. So there is a change in volume when the system changes from its intermediate state to the final state, and because of the change in the temperature, this occurs at constant pressure, and it is expressed in this manner. So essentially, by introducing an intermediate term, we have now been able to express the overall change in the state of the system in terms of a constant temperature transition and a constant pressure transition. More importantly, we saw that, or it is possible for us to conceive that this change in the volume with respect to pressure. So the change in the volume of the system when you change or when you impose a pressure or release the pressure can be treated as the compressibility. So this is just something that we considered during our last discussion as well, compressibility. And similarly, this change in the volume with respect to temperature when you heat the system or when you cool the system can be referred to as the thermal expansion. So these are rather constants that are involved with the overall change in the state of the system. So essentially what we are doing is we are expressing the change in the state of the system as a product of a constant and the change in that particular fundamental variable. So if I assume this constant to be A and this constant to be B, then essentially I am including these constants here, and the whole change in the state of the system is dependent on the change in the state variables alone. So this is a way of further simplifying your expression and relating it to the physical condition. So when you consider a system and when you know the compressibility and the thermal expansion of that particular system, then by just considering the change in the pressure, if we are able to measure that, and by considering the change in the temperature, which we will be able to estimate. So by just considering the change in the pressure and change in the temperature and including these constants that are known to us because these are material constants, we will be able to calculate the entire change in the volume of the material. So again, we need not be worried about the partial derivatives that are involved here, which are too difficult to calculate in a physical condition. So in a physical condition, these partial derivatives can be replaced by a material constant, and by involving these material constants, the change in the state of the system, the change in the volume of the system can be calculated by just considering the change in the pressure, which can be measured, and change in the temperature, which can be measured again. Now, this is what the advantage of translating or replacing the fundamental variables from the path variable or path function to state function gives us. It helps us simplify the transition by considering or by breaking down the overall transition from one state to another into simple transitions involving constant temperature and constant pressure. Now, let us use the same approach for this particular change in the state of the system, which is now described by the change in the internal energy. Here it is the change in the volume, and here it is the change in the internal energy. Now, if you consider the change in the internal energy, again, instead of being represented by Q and W, that is the heat transfer and the amount of work done, now it is being written as the change in the internal energy in terms of temperature and volume. So we have considered this in the previous slides. Now we will take the initial state to be U1, that is associated with T1 and V1, and ideally it directly translates to U2, that comprises of T2 and V2, now that is characterized by T2 and V2. Now since these are rather state variables, we are allowed to take a detour and we are introducing an intermediate state, and this intermediate state, it assumes the temperature to be constant, and the temperature is similar to that of the initial state, and the pressure or the volume has now reached its final state. So essentially the volume has changed from U1 to U2 while the temperature is constant. And in the second case, the temperature is changing from T1 to T2 while the volume is constant. So we will consider a setup like this, but this is primarily because we have written the overall change in the internal energy of the system in terms of the state variables. This is possible because we have written it in terms of the state variables. So now, like we have represented the overall change in the volume in these partial derivative form, we will also be able to do that for the change in the internal energy of the system. So the overall change in the internal energy of the system can be expressed as something like this. We have in the initial step the change in the volume from V1 to V2, and we have a corresponding change in the internal energy because of the change in the volume, and this happens at constant temperature. And similarly, we have at the second step there is a change in the temperature from T1 to T2, and because of that there is a change in the internal energy, and this happens under constant volume. And now what we have is we have a setup or an expression that is similar to what we have seen in case of change in the volume that represented or that kind of related to the change in the state of the system. So initially we described the change in the state of the system using volume. Now we have described it in terms of internal energy, and this internal energy, it involves both heat and the work done. Now let us consider this term here. So what we have is change in the internal energy of the system at constant volume. So when you consider, so again this we saw in the previous lecture as well, when you consider the change in the internal energy of the system at constant volume, so the description of the change in the internal energy of the system, du, if you consider a very small change in the internal energy of the system, it is expressed in this manner: change in the heat transfer or the amount of heat transfer and the work done in the system. And when you have a constant volume, like the second term here, when you have a constant volume, it means there is no work done on or by the system. So essentially what you are left with is the change in the internal energy is equal to the amount of heat transfer that is occurring at that transition. So in this transition, that is in the transition 2, that is represented by the second term here, the change in the internal energy that happens as a consequence of the change in the temperature is equivalent to the amount of heat transfer. So in that case, what we have is this partial derivative of the change in the internal energy is nothing but the change in the heat or the amount of heat transfer to that of the change in the temperature. So dq is the amount of heat transfer, or it can also be written as this change in the heat transfer or amount of heat transfer, that is d can be removed. So it can also be written as, so it is the more accurate way of writing it, but since heat transfer is, so if you assume you start from 0, initially there is no heat transfer and you introduce a specific amount of heat, then essentially what you are doing is, if you introduce a specific amount of heat, say q, essentially you are considering q minus 0, so dq and q minus 0 is nothing but q, because initial state of the condition is there is no heat that is involved and you are introducing dq or heat of q, then since the initial there is no heat that is being involved, there is no heat transfer that is being involved, so the initial state is 0 and the final state is q, so dq is nothing but q, and what you end up having is q by dt. Now at the constant volume, again this all operates under the constant volume assumption. The change in the internal energy with respect to the change in the temperature is the ratio of the heat transferred into or away from the system and the corresponding change in the temperature of the system. Under constant volume, again what we have is, when you consider the change in the internal energy of the system with respect to temperature, it is nothing but the ratio of heat transferred into or away from the system and the corresponding change in the temperature, again under constant volume. So this change in the temperature, this ratio of the amount of heat transferred into or away from the system and the change in the temperature, the corresponding change in the temperature, is referred to as heat capacity. Under a general case, irrespective of constant volume or constant pressure, in a general case, when you consider a system and you feed or when you consider the heat transfer associated with it, the heat transfer can be into the system or away from the system. The associated temperature change is measured and you take the ratio of the heat transfer and the change in the temperature. This particular ratio is referred to as the heat capacity. Now here we have arrived at this ratio by considering or by assuming constant volume, so we have to have a subscript V here. So essentially this particular change, the change in the internal energy that is brought about by the constant volume consideration and the change that is due to the change in the temperature, can be expressed as the product of the heat capacity and the change in the temperature. So we saw when we considered the change in the volume that translated to the change in the state of the system, the overall change can be written as the product of a material constant and a change in the variable, change in the state variable. By considering a similar, by treating the change in the internal energy of the system in a similar way, we have arrived at similar expression. And now for constant volume, we have replaced the change in the internal energy in terms of the change in the internal energy under constant volume with respect to the change in temperature. We have translated it as the ratio of the amount of heat that is being transferred into out of the system and change in the temperature. So because of this ratio is consistent, or this ratio describes the heat capacity of the system at a constant volume, we are now able to express or quantify or measure this particular change in the internal energy of the system as a product of this constant and the change in the temperature. Now what is left for us is this particular derivative here. So this particular derivative here, that is change in the internal energy of the system with respect to the change in the volume at constant temperature. So essentially what we are having is, we are assuming the temperature is constant, however there is a change in the volume of the system, and because of that there is a change in the internal energy. So such a consideration is referred to as the isothermal consideration. Now, unlike the previous partial derivative, that is the ratio or that which considers the change in the internal energy of the system with respect to the change in the temperature, this partial derivative that relates change in the internal energy of the system with the change in the volume cannot be quantified as a specific constant. So the reason for it is because if you consider the different changes that occur in a system when the internal energy of the system changes with respect to volume, it is not that straightforward as in the case of the change in the internal energy with respect to temperature. So let me repeat, like it was possible for us to translate this change in the internal energy of the system with respect to temperature in terms of the specific constant, the same cannot be done in this isothermal condition. Because if you consider, so essentially what we are considering or what we are doing is, even though we have changed the variables, the system that we are considering remains the same. So in order to arrive at this partial derivative, essentially we have changed the variable that dictates, the couple of variables that dictates the internal energy. In order to arrive at this partial derivative, we have changed the variables that dictate the internal energies from heat and work to temperature and volume. Despite these changes, we still consider a system wherein both heat and work are operating simultaneously. Even though we have translated our variable, we have changed our variables, we still are operating in a system that allows for both heat and work to be done on or by the system. So what does then change in the internal energy with respect to volume means? So let us consider that. So when you consider the change in the internal energy with respect to volume, what it essentially means is that in order to ensure the temperature to be constant, you are allowing the system to change its volume. So you are, supposing we will assume a case wherein you are feeding in heat. you are feeding in heat and the work is done by the system. Okay, so we are feeding in heat and the work is done by the system. This is also positive individually and this is also positive individually. So individually the heat is fed into the system and the work is done by the system. Now the combination of these two in an adiabatic state would tremendously increase the temperature. So heat being fed, it ultimately translates to the increase in temperature. Now the work is done by the system. So if you consider the microscopic state of the entities, so let us begin by considering the system is comprising of gases. So you increase the kinetic energy of the gaseous atoms, so that means the temperature is increasing. So when you don't allow the system to expand, you assume that the system is not allowed to expand and you just considering an adiabatic system, what essentially happens is that the temperature tremendously increases. Now what we are doing in order to avoid this increase in temperature, we are allowing the system to expand. So we don't want to have an increase in temperature, we want to maintain the temperature to be constant because we are ultimately considering the isothermal condition. So even though the heat is fed into the system and work is done by the system, both contributes to the increase in temperature, we are allowing the system to expand in order to ensure that the overall change in the temperature remains constant. And when we do that, because we are considering a gaseous system, the amount of volume expansion will be considerably high, and because the amount of volume expansion is considerably high, the denominator will be considerably high, and this overall change in the internal energy with respect to the volume will be close to zero. Again, we are assumed that the system is made of gas. So instead of treating this partial derivative as we have treated the similar partial derivative for the constant volume, we are now considering, or we are trying to understand, rather gain a conceptual understanding of what this partial derivative means. Since there is not really a specific constant that we can attribute this particular partial derivative, we are trying to gain a conceptual understanding of what this partial derivative means. So this partial derivative, it means that we are allowing the system to expand. So despite the amount of heat that is being fed into the system, despite the work that is being done by the system, we are allowing the system to expand in order to ensure that the temperature is constant. So because we are allowing the system to expand in such a way that the temperature is remains constant, the amount of the expansion, the change in the volume, in order to ensure the temperature is constant, particularly in the case of gas, will be significantly higher, and therefore it is close to zero. This particular term becomes close to zero, again in the specific case of gas. However, if you translate this particular system, or if you consider, or if you replace this gas with solids, what essentially would happen is, despite the amount of, if you consider the same amount of work done, if you consider the same amount of heat transfer, the amount of change in the volume will be significantly lower. So in case, depending on the nature of the system, the way this particular partial derivative is quantified, it changes, and that's the reason why we don't have a specific constant for it, and therefore we need to go for a conceptual understanding. So when you consider a system that is made of gas, and you impose, or when you introduce a heat of Q and the work W is done by the system, then the combination of these two, in order to avoid the increase in temperature, will ultimately result in a huge increase in the volume of the system. So in that case, the partial derivative, that is the change in the internal energy with respect to the volume, that is the change in the volume which is in the denominator, will be lower. This is in case of gas, close to zero. Now in case of solid, the same amount of heat and the same amount of work done will not give you that much change in the volume, because unlike gas, we don't have enough space, or the atoms or the entities that constitute the gas or the solids, atoms, molecules, whatnot, ions. So all these, they are closely packed in solids, and also in fluids as well, unlike gas in solids and most fluids. Since the atoms or molecules or ions are closely packed, despite the introduction of the same amount of heat and work, you will not be able to observe a similar change in the volume. So what then happens to this amount of work and heat is that it significantly increases the internal energy of the system. So in that case, the denominator would be lower, the numerator would be higher, so the partial derivative will be considerably larger. So in case of the isothermal condition, what happens is the partial derivative that talks about or that consider or that expresses the change in the internal energy of system with respect to volume, it varies depending on the system. And if you categorize the system as solids, fluids and gas, in case of solids and fluids, since the expansion or the amount of volume expansion that is possible is rather restricted for a given amount of heat and work done, the denominator becomes lower and the entire introduction of these work done and heat will translate into the change in the internal energy. So this term will be predominantly higher, significantly higher. However, in the case of gas, since the atoms are allowed to move about freely, the volume considerably increases, so therefore this particular derivative is lower. So this is something that we can conceptually understand about this particular variable here. So it means that depending on the state of the system, the role of this particular variable varies. In case of gas, this role can be more or less ignored, and in case of solid, this particular the partial derivative here plays a dominant role. So here we have been able to reduce this particular partial derivative into a constant. However, this is not possible in this case, so therefore we have gone with gaining a conceptual understanding of this particular partial derivative. Now, so based on our understanding of this constant and the particular partial derivative, we will be able to at least estimate or will be able to say which of these two partial derivatives are dominant. So in case of gas, all you need to consider is this variable here, and in case of solid, you need to give importance, a prime importance to this variable or this partial derivative here. Now, what we have seen is we have considered a constant volume condition and a constant temperature condition. So in this context of discussing the change in the internal energy of the system, we have considered isothermal condition here, and we have considered a condition where there is not much change or there is no change in the volume. So what is now left is the isobaric condition. So the isobaric condition is nothing but, bar is used here, so it is constant pressure condition. So far what we have seen is, we have seen constant volume, delta U under constant volume. We have seen delta U, that is the change in the internal energy, under constant temperature. Now let us consider the change in the internal energy under constant pressure. Isobaric delta U under constant pressure. Now again, let us move back to our conventional first law of thermodynamics. That is, it states that the change in the internal energy of the system is when you have a combination of work done and heat transfer. This is expressed in this manner. Again, at least for my understanding, or to me, is the more appropriate way of expressing it. And when you do that, we can since the pressure is constant, we can adapt the conventional description of our work done, which is P dot dV. So this is the conventional description of our work done, and we can introduce this here. So let us assume that the pressure is constant and the change in the state of the system, that is U1 to U2, it is in a way characterized by the change in the volume from V1 to V2. So under constant pressure, there is a change in the volume from V1 to V2. Now in such a case, delta U can be expressed as, which is nothing but U2 minus U1. Again, the state variable, which is nothing but q plus, or rather we will consider the minus here, the integration of V1 to V2 P down dV. So the P pressure is constant, it can be taken out, and let us assume that instead of taking any detour while the work is being done, the volume 1 is directly being, or it is taking the shortest path, or it is taking the straight path to V2. So if you consider our previous plot of pressure and volume, so instead of taking any other path, it takes rather the path from V1 and V2, it takes another path from V1 to V2, the direct path from V1 to V2. Therefore, the overall work done is the area under this particular rectangle, let us say. So that means this can be expressed as P V, V2 and V1, and then this other will lead to P V2 minus P V1, and you have U2 minus U1. So essentially we have made some simplistic assumption. We have assumed that the transition from V1 to V2 is rather straightforward, and then the pressure is constant. Now essentially what we can do is we can rearrange these terms, and when we rearrange these terms, what we end up having is Q is nothing but U2 plus P V2. So we are rearranging these terms and clubbing the variables that are associated with the second state of the system together, and the variable that are characteristic of the first state of the system together. So you bring these V2 here, so we have a minus sign and it becomes plus when you bring it to the right hand side, and similarly you bring this term here, so this minus here and minus here, it becomes plus, and you bring this here, it becomes negative, and you take this minus out, you end up having an expression like this. So you have clubbed the variables associated with the final state here and the initial state here. So initial and the final state. Now these two terms can be referred to as using a specific variable. Let us refer to these two terms using a specific variable, let's say H2 and H1. And ultimately then the heat that is introduced or taken out of the system is nothing but the difference between these two variables. So what we have done is, since these are the different variables, different state variables, and we have a constant here, we have introduced another variable and expressed the heat or the change that is introduced in the system because of the heat alone instead of these variables. And ultimately this renders us this expression here, and this variable here is what we refer to as enthalpy. So let us just have a quick review of what we have done. So we began with a consideration of a constant pressure case. So we have a system wherein the work is done on it or by it, and there is a heat transfer associated with it, maybe into the system or away from the system. And we began with our the first law of thermodynamics, which we are now familiar with. And when we began with the first law of thermodynamics and assume this constant pressure condition and the change in volume, and we keep the heat transfer as it is, then we end up with an expression that relates the heat transfer to a difference in a particular variable. Now the question is this variable state or is a path variable? Now again, in order to identify if a variable is state or a path variable, we have a simplistic criterion. In order to describe a variable, if you need the history of the variable, if you require the history of the variable, then that variable is a path variable, it's not a state variable. On the other hand, if in order to estimate, in order to quantify, in order to express a particular variable, you do not need the history of the state of the system, you do not need the history of that variable, but at the present state, what is the value of the variable, then it is the state variable. So if you consider this expression here, the H2, which is equal to the H2, it can be written as equal to the internal energy in the second state of the final state, and the product of the pressure and the volume of the final state. So if you ignore these states and consider, assume just if you want to calculate the enthalpy in a particular state, if you ignore the state, any state, this is possible. So you can just change it to I. So this is possible for any state. So you are just considering a set of or three state variables. You are not considering any history of the system. You are just considering state variables that can be measured for a given system in a particular state, and you are combining it. You are just doing some numerical operation to it, and you are ultimately arriving at another variable. And therefore, because of this dependency of this particular variable, which can be calculated or which can be estimated, or it does not depend on. So none of these variables, be it internal energy, be it pressure, be it volume, since none of these internal energy, they depend on the previous state of the system. Since the history of the system is not required in it, we can refer to as the ultimate variable that comes out of all these, the ultimate function that comes out of all these variables as the state variable. Again, it is also possible that combination of two path variables leads to a state variable, but that is a thermodynamic relation associated with all these variables. So here we have combination of two path variables leading to a state variable. However, here again we are talking about change in the variable, not a description of a specific variable, but a change in the variable. So that is something you need to understand. Just because on the right hand side of an expression you have combination of path variables, that doesn't mean that on the left hand side of the equation you have a path variable. So you need to understand what is the meaning associated with the expression. Here we are considering the change in the state of the system. We are expressing the change in the state of the system with respect to two path variables. Here we are just replacing this expression here with one of the term, and this term we refer to as enthalpy. And here we don't consider a thermodynamic significance yet. We will be attributing some thermodynamic significance to enthalpy later, but here we are just considering this combination of term as a variable, and therefore this is nothing but a state variable. So essentially what we have seen is, in a system like this wherein the work is allowed to happen, the heat transfer is allowed to happen, when you want to see, or when you want to calculate, or when you want to describe the change in that is brought about in the system exclusively because of the heat transfer. So you have a system where the heat transfer is possible, the work done is also possible, and in that you want to just calculate the change that is brought about by the heat transfer, then it is nothing but the difference in the change in the enthalpy of the system. So in case of combination of both heat and work, the change in the state of the system is described by change in the internal energy of the system. In the similar system, when you want to calculate the change in the state of the system primarily due to the heat transfer, then it is achieved by change, or this is calculated by change in the enthalpy of the system. So with this, I would like to wind this lecture up, and we will continue from this. We will try to understand what is the importance of enthalpy in the subsequent lecture. So goodbye.